Okay, we're back to do some more force solving problems. We're working on how to solve problems that involve multidimensional vectors and components of forces. So let's do an example involving Halloween candy, since Halloween is getting close. So let's imagine that you and I are wrestling over a 5-kilogram bucket of Halloween candy. I know that's a pretty lightweight bucket, but you know, we gotta make these problems simple enough to understand. So suppose I pull the bucket at a 45-degree angle with a force of 24 newtons, and you pull the bucket at a 70-degree angle with a force of 31 newtons. And as we pull, the bucket is hanging in the air. And ultimately what I want to know is who wins this game. That is to say, what is the net acceleration on the candy bucket? Is it towards you or is it towards me? Now, as with most physics problems, we've been told some information here, and you have to actually do some interpretation and set the problem up such that you can solve the problem. You have to introduce coordinates, you have to place the people, but the way you do it or the way I do it may not be the same, but it doesn't matter. In the end, the conclusion of the problem has to be exactly the same. One of us is going to win, and that person who wins will be the one that is in the direction of the net acceleration. Okay, so let's go ahead and set this problem up. As with all physics problems involving forces, the very first thing we do is we draw a free body diagram. So the free body diagram for the bucket of candy will start with an object to represent our bucket. And the very first force I always put on, because I know it's there, is the weight of the earth pulling on the bucket. I told you the mass of the bucket, so I can calculate the magnitude of that force. It's the mass times the acceleration due to gravity. And then there's two people pulling on the bucket. We said that I was pulling on the bucket at an angle of 45 degrees. So this is the force of Larson on the bucket. And we're told the magnitude of that force. We're told that the magnitude of that force is 24 newtons. And you are also pulling with the bucket with a force of 31 newtons. And so your force goes in the opposite direction. This is the force of you on the bucket, and that's equal to 31 newtons. And then what we're told as part of the problem statement is the angle at which we are pulling those two forces. I'm pulling at an angle of 45 degrees, and you are pulling at an angle of 70 degrees. Okay, and I probably haven't drawn those angles quite accurately, but that's why I mark them so I don't forget what they're actually doing. And so you can see that this problem is a multidimensional problem of the form that we've encountered before, where there are some forces that point in what you and I would normally call the vertical direction, plus y, and there are some forces, or components of forces, that point in what we would normally call the horizontal direction, plus and minus x. Okay? So this is clearly a 2D problem. None of the forces are related or orthogonal or any of that, so I can choose those standard coordinates with impunity. And so the very first thing I'm going to do in this case is I'm going to break all of these forces up into their components. Because what I want to do is I want to use Newton's second law written down for each component in the problem, the vertical direction and the horizontal direction, and I'll use those components to solve the problem ultimately. So let's just write down the force of Larson on the bucket, what the components of that force are. Okay, so the force that I'm exerting on the bucket in the x direction is equal to the magnitude of the force that I exert times the cosine of 45 degrees. And if I numerically work that out, I use that 24 newtons and I multiply it times the cosine of 45 degrees, I get 16.97 newtons. And if I do the same thing in the y direction, so it's the magnitude of the force that I exert times the sine of 45 degrees, I get 17.0 newtons. Now, These two numbers are exactly equivalent. I wrote this with 4 significant figures here and this with 3 significant figure here. We're actually going to use the 17.0 newtons. I just wanted you to see how close or how different your answer can look depending on how many figures you actually write out with. Okay, so that's the force that I exert on the bucket. And let me go ahead and write out the components from the force that you exert on the bucket. So the force that you exert on the bucket in the x direction is equal to the magnitude that you exert on the bucket times the cosine of 70 degrees. And if I use that 31 newtons that you exert on the bucket and I multiply it times the cosine of 70 degrees, I get that the x component of the force that you exert is 10.6 newtons. And similarly, if I look at the y component, that's the force that you exert on the bucket, that's 31 newtons, times the sine of 70 degrees. And if I work that out, that's 29.13 newtons. Okay? Now, as is my usual habit, I'm writing down the numerical value of the components here in terms of its absolute value. I will impose the sign on these components when I use Newton's second law. So let's go ahead and do that now. So Newton's second law is that the sum of the forces in the x direction is equal to the mass of the bucket times the acceleration in the x direction. The acceleration in the x direction is unknown. This is what I'm actually trying to find. And so the sum of the forces in the x direction is the force that I exert on the bucket in the x direction, that is in the positive direction according to my coordinate system that I've drawn here, minus the x component of the force that you exert in the direction. That's the force you exert on the bucket in the x direction. Okay? And similarly, I can write the sum of the forces in the y direction. That's equal to the mass of the bucket times the acceleration in the y direction. Again, unknown, something that we need to figure out. And this is equal to the force that I exert on the bucket in the y direction plus the force that you exert on the bucket in the y direction. Both of those are in the positive direction upward, in the plus y direction, and minus the weight. So this will be minus the mass of the bucket times little g. Okay? So those are my Newton's second law equations. And so now I can simply insert all of the numbers. So in the horizontal direction, in the x direction, I have the sum of the forces in the x direction is equal to the force that I exert on the bucket, which up here we computed was 17.0 newtons, minus the force that you exert in the x direction, that's 10.6 newtons, and that overall is equal to 6.40 newtons. It is positive, so the net force in the horizontal direction is in the positive direction, which is towards me in terms of our picture. Okay, so now we can do the vertical direction. So this is the sum of the forces in the y direction. So that is equal to the force that I exert on the bucket in the y direction, that is 17.0 newtons, minus the force that you exert in the y direction, that's 29.13 newtons, plus, and then minus the weight of the bucket, m times g. And so the bucket we said was 5 kilograms. If you multiply that by 9.80 meters per second, you'll get that that is 49 newtons. And so the sum of the forces in the y direction is overall equal to a minus 2.87 newtons. Okay, so the acceleration is in the downward direction. Okay, So now what the problem asks for is who is going to win the battle. Well, I know that the net force is towards me and towards the floor, so it looks like I'm going to win the battle. And what we want to know is what is the acceleration. So the components of the acceleration, the component of the acceleration in the x direction is the sum of the forces in the x direction divided by the mass of the bucket. So that is 6.40 newtons divided by 5.0 kilograms. And so the acceleration is 1.28 meters per second in the x direction towards me. And the acceleration in the y direction is the sum of the forces in the y direction divided by the mass, which is equal to minus 2.87 newtons, again divided by 5 kilograms, and that is equal to minus 0.57 meters per second. Okay, so the ultimate result, as if you expected anything less, is that I win the candy battle, but that the combined forces of the two of us are not enough to keep the bucket suspended. Okay, so that's the end of that problem. Happy Halloween. Good luck trick-or-treating and getting some more candy since I won all this candy, and we'll talk to you again soon.